In this lesson, we're going to look at dilution calculations. So when I dilute something, water is added to that. So when I add water, that changes the amount or volume of my solvent, but it does not change the amount of solute that I have. So if I'm only adding water, which is the solvent, it will change my overall volume of solution, but it doesn't change my mass of solute, which means it also doesn't change my number of moles of solute. So my volume increases, and if concentration is equal to number of moles divided by volume, if my mass of solute or the number of moles of it doesn't change, but my volume increases, if I divide by a larger number, then my answer is going to end up being smaller. So as the volume increases, the concentration is going to decrease. Just a visual here. So if I start off with a certain concentration of solution and I add water to there, my overall volume increases. My solute is now going to be dissolved in a larger volume, which means if I look at a specific volume within here, in the more concentrated solution, there are going to be more molecules of solute than there are in that same given amount of volume in the more dilute solution there. So in the initial versus diluted solution, so the number of moles of solute don't change. So there's no addition of solute, only addition of water, which means more solvent and then also more overall solution. So the volume changes, but the number of moles of solute are the same in both. So to calculate number of moles, that is equal to concentration times volume. So if my initial number of moles is equal to my final number of moles, then that means when I multiply my initial concentration and volume, that needs to equal whatever my final concentration and volume multiplied give me. So my initial concentration times initial volume gives me my number of moles. My diluted concentration times my diluted volume also gives me the number of moles, and because my number of moles hasn't changed, those two are equal to each other. So concentration initial and volume initially multiplied are equal to my final concentration times my final volume. And I can use this to calculate any one of these variables. So this is what I will use when I am using from a stock solution of hydrochloric acid, which is generally a 12 mole per liter solution. So if I know my initial concentration and I know the concentration and volume of hydrochloric acid that I want to have, so often I will use a 0.5 mole per liter solution or a 1 mole per liter solution for labs in the classroom. So if I know my concentration and if I know the volume that I'm going to need to make to have available for students, then I can work backwards to calculate what volume of that 12 mole per liter solution will I need to create the 1 mole per liter solution. So what is the molar concentration of a solution prepared by diluting 0.180 liters of a 0.600 mole per liter or molar solution of nitric acid to 0.540 liters? So I am diluting this amount of this concentration solution to this amount. So what I'm looking for is the concentration. So this is an initial volume, this is an initial concentration, and this is going to be a final volume. So that's the first thing, is to identify whether each of these values is a concentration or a volume and whether they are initial or final amounts. So concentration initially 0.6 molar, the volume initially 0.18 liters, and the final concentration is what we need to find. and then the final volume is 0.54 liters. So I'm going to set up my equation first, and then I'm going to input those values. So I have C1 V1 equals C2 V2. C2 is what I'm solving for, which means I want to isolate that. So I have this as a multiplication, which means to move the volume of my final solution over, I'm going to need to divide by that. So my final concentration is equal to C1 V1 divided by V2. So then I'm going to input those values, and once I calculate that, I have a 0.2 mole per liter solution. Okay, next example, how much water needs to be added to 15.0 mils of a 1.8 molar potassium hydroxide solution diluted to give a 0.3 mole per liter solution. So how much water needs to be added? So I'm going to need to know my volumes and concentrations to calculate the final volume, and then I'm going to need to figure out the difference between those volumes to determine how much water is added. So I'm starting with a 1.8 molar solution of potassium hydroxide, and I have 15 mils of that. Divide that by 1,000 to convert to liters, so 0.015 liters of potassium hydroxide. And I want to end up with a 0.3 mole per liter solution of that. So I need to figure out what my final volume is. Once I figure out what my final volume is, the difference between my initial and final volumes is the volume of water that is added. So when I find my volume of the final solution, that is the volume of the total solution. The difference between initial and final will give me my volume of water that was added. So C1 V1 equals C2 V2. I'm looking for V2, so I need to divide by C2 to move it to the other side. So there is my formula. My final volume is initial concentration times initial volume divided by final concentration. So plug in my numbers, and that gives me 0.090 liters. So remember, that is your final volume. That is not the amount of water that was added. So we were asked how much water needs to be added. So initially, we started with 15 mils of solution. We now have 90 mils of solution. So the difference between those is 75 mils. So that is how much water was added to the 15 mils, which is what diluted it from a 1.8 mole per liter to a 0.3 mole per liter solution.